Earth scientists study the four major spheres of Earth processes. The hydrosphere, which involves all water on Earth in solid, liquid, or vapor form. The biosphere, which involves all life on Earth. The geosphere, which involves the solid part of the Earth from its surface to its core. And the atmosphere, which involves the layer of gas that envelops the Earth. Earth scientists study processes that occur in the intersection between the atmosphere, hydrosphere, biosphere, and geosphere. In this unit, we will focus on applications of quadratic and polynomial functions that Earth scientists use to understand human interactions with groundwater at the intersection between the hydrosphere and the geosphere.
The water cycle describes the continuous movement of water on, above, and below the surface of the Earth. One component of the water cycle is groundwater, which provides water to large populations around the globe for drinking water, agricultural use, and industrial applications. Groundwater is water found underground in the cracks and pore spaces in soil, sediments, and rock, and supplies drinking water for 51% of the general population and 99% of the rural population of the United States. We also rely on groundwater to help grow our food. In fact, 64% of groundwater used in the U.S. is dedicated to crop irrigation. Groundwater is closely linked to overlying rivers and lakes with which it can exchange water. Although groundwater is a part of the water cycle, it is in limited supply. The water cycle will eventually recharge groundwater reserves over tens of thousands of years, which is longer than the span of a lifetime, and even a civilization. In some places, fresh groundwater reserves are already depleted. Within a century, nearly half of Earth's groundwater reserves are expected to be depleted as well. Why does it take so long to recharge groundwater? The answer can be found in understanding how groundwater interacts with the geosphere. Rocks have open spaces in them known as pores, which is where water can be stored. The interconnectedness of these pores controls how easily water can flow through them, a property called permeability. The higher the permeability, the easier it is for water to flow through the rock. A permeable rock body that holds water in its pore spaces is known as an aquifer. Because the water has to navigate through small channels in the rock, it can take hundreds and even thousands of years for water to move through an aquifer. To describe water availability and movement through time in groundwater and rivers, Earth scientists use hydrographs. Hydrographs are graphs of water level or flow through time. Do you notice that the shape of this graph resembles that of a polynomial function, where the water flow changes through time are represented by alternating increasing and decreasing intervals? An Earth scientist could construct a polynomial function that fits these data, and then use the graph to understand what variables could be impacting water flow as they continue to take measurements through time. This will allow a greater understanding of how we can better manage our resources. Groundwater is stored in confined or unconfined aquifers. In unconfined aquifers, water infiltrates from the surface through open pore spaces and is stored in the subsurface material. Confined aquifers, however, have impermeable layers of rock above and below that act as seals preventing water movement. When groundwater is pumped out of a well in an unconfined aquifer, a cone of depression forms around the well. Cone of depression is a term that describes the lowering of the water level surrounding the well, which can be modeled using a parabolic function. As groundwater is pumped from the well, the cone of depression will deepen and widen. Because of this, it is sometimes necessary to move the well to a new location if the cone of depression becomes too deep to pump water from. Understanding the shape of the cone of depression through time is critical to regulating water usage. When groundwater is pumped out of a well in a confined aquifer, the removal of water surrounding the well, caused by water being suctioned from pore spaces, pulls the overlying rocks downward, causing a depression at Earth's surface in a process known as subsidence. The shape of the land subsidence can also be modeled by a parabolic function. Subsidence is an expensive consequence of groundwater overuse. California's Fremont-Kern Valley Canal delivers nearly 3 billion cubic meters of water to over 18,000 farms across the Central Valley every year. Groundwater overuse has caused the canal to subside at a rate of 1 inch per month, reducing water flow through the canal by up to 60%. Repairing the canal's damage caused by subsidence will cost taxpayers an estimated $400 million. It's clear that human water usage can cause significant physical changes in water reserves and rock structure both above and below Earth's surface. But how does human interaction with the hydrosphere impact water quality? Many different pollutants threaten the quality and safety of water supplies around the world. Throughout the United States, one of the major threats to water supplies comes from pollution caused by historical mining activities. In August of 2015, a spill occurred at the Gold King mine near Silverton, Colorado, when 11 million liters of acidic waste were inadvertently released from the 100-year-old mine into the Animas River. The mine waste contained high concentrations of heavy metals, particularly lead, arsenic, and iron. Following the spill, Earth scientists closely monitored the water chemistry of the Animas River at multiple sites downstream of the mine. Because of this close monitoring, we have a clear picture of the heavy metal contaminant pulse through each monitored location, which can be described by a parabolic function. By mathematically describing the shape of the contaminant pulse, Earth scientists were able to predict water quality improvement at each location. Scientists often combine knowledge of the water cycle and the physical and chemical changes that occur as a result of human impacts to gain a better understanding of water availability and safety in the future.
Hi, my name is Dion Knights. I am a PhD candidate in the School of Earth Sciences at The Ohio State University. I study hydrogeology, so hydro is related to water, geo is related to the earth, so I study water on earth or the water in earth, such as groundwater. I would like to work at a national laboratory and do research on groundwater resources. So we use different sensors such as pH and temperature sensors. We also use wells. And if you have a well inserted into a shallow aquifer and you're pumping off that well, what you would observe over time is a cone of depression forming around the well. And that is essentially a parabola delineating the water table that develops over time. I also use some remote sensing techniques using satellites and aerial images. And I use some modeling techniques, which essentially uses polynomials and quadratics like the advection dispersion equation. So we use several different tools. One of them is called a beep tape, which is very fun. It's pretty much a long reel of tape with markings letting you know what length you're at. And what we do is we reel that down into a well, and at the very tip of that beep tape, there is a sensor. And when it gets into contact with water, it beeps. It makes a loud noise. So that is called a beep tape. And once we measure the length of the tape, we'll know how far down the water table is. We also collect samples just using syringes, and then we take that back to the lab, and then we run those samples for nitrate or ammonium or other nutrients that could be in the water.
Water is one of our most important natural resources. Without it, there would be no life. Although there is plenty of water on Earth, it's not always in the right place, at the right time, with the right quality, due to population growth, pollution, and increased energy demands. To make sure we have enough safe water available to those who need it, it's important for us to conserve our water resources and do our best to avoid polluting them. Earth scientists play a major role in water conservation and safety efforts by monitoring the water cycle. Studying different aspects of the water cycle allows Earth scientists to help effectively manage this vital resource and match the natural supply of water with human demands.